So we'll implement the general tree in the next few videos. In this first one, we'll talk about how to build up a tree. And we will take the same approach that we used when we build our linked list that store data. Namely, the first thing we'll do is to implement the tree node and a tree that manage the tree structure, but we're not going to have data in this tree just yet. And the next step will build a tree that inherits from the tree that manage structure and add data to it. Now, obviously, I have had the code typed out already, so I have the tree node implemented, and I have the tree itself implemented all the way up to adding a node to the tree. I'm not going to go through typing out the code on the video itself because that would take up too much time, but I will explain what each of the method does. So the first thing we'll implement for the tree is the tree node. We call it the FhTree node. FH is kind of short for foothill. And what it needs to do is it needs to contain 3 pieces of information, as we explained earlier. So it has to have the sibling reference, a pointer, first child, as well as a previous pointer. Now, it also has a root attribute, and it is basically the root of the tree that this node belongs to. And the reason it's there is mostly for validation, which I'll explain in a bit. And lastly, an attribute that it will have is label. This is just to help us to identify the node when we print out a tree, because otherwise, without any data, it's really hard to distinguish one node from another. So all of these attributes, they can come from the parameter that the node is given when it's instantiated. Now, all of them have a default value of none, so all of them are optional. And lastly, the dunder string method for the tree node, we basically return the label, which again would help us to see which node we're talking about. And it kind of helps to have the ID there too, just as in the case of a linked list node. Now, one last thing I want to mention is, as you can see, we are going to just access these attributes directly because, well, I just want to focus on the concepts. Ideally, we want to use setters and getters, but the good thing is with the Python properties, we can define those later if we have to without changing the code that we already will have written by then. Next, we will implement the tree itself, or at least the part that manages the structure of the tree. We'll call it the FhTree. And the methods that we'll implement, first, always the initializer, and then we'll implement the method to insert nodes to the tree. Then we'll implement the dunder string method so that we can see the tree. And finally, we'll implement method to remove nodes from the tree. And then we'll add other helper methods along the way. So now we can talk about the dunder init method, which is usually used to set up all the attributes of a given class. Now, in this particular dunder init method, it calls another method called clear. The reason it does that is that if the client code wants, then it can call the clear at any time to kind of reset and rebuild the tree from the ground up. Okay, so inside the clear method, it initializes 2 attributes. The first is, well, the most important node of a tree, that its root, right? So from the root, it can get to all the other nodes in the tree. Now, when we first initialize the tree, obviously we don't have a root yet, it's an empty tree, so it is set to none. The other attribute clear sets up is the size of the tree, which is, if you remember, the number of nodes. So number of nodes is very, very useful for debugging and other purposes. And finally, you can kind of see that both attributes has a m underscore in front of it. They are just there for kind of a historical reasons that we really need not to concern ourselves with, but just that they're there. Next, we'll talk about a couple validation methods implemented for the FhTree class. So the first such method is called valid node. So it's useful to validate a given object is indeed a node. So if it's not the node is not an instance of the tree node, then it raises a type error. And the second one is it's also useful to validate that a given node is part of the tree. So first it validates that the node is a node, and then it checks that the root of the tree, if it is the root of the given node, and if it is not, then there is a problem. So as you can see, we're definitely not using duck typing in our tree implementation because we're checking for types. Now we're ready to actually add a node to the tree. So the first node we should add to the tree is, well, the root. Right? So we'll make a method specifically for that. We're going to call it setRoot, and it will take a node and we'll make it the root of the tree. So in order to do that, we'll set the two attributes of the tree properly. First, we set the root of the tree to the given root node. Next, now that we have one root node, we'll set the size equal to 1. And finally, don't forget to set the root attribute of a new node and the root of the tree that the root node is in is the root node itself. So we'll set it to be that. Now, the next thing we want to do to build a tree is to add child nodes to the root. Now, root is just one of the many parent nodes in the tree. So in general, we really need a way to add a child node to a parent node. Then the question is, well, where among the list of children of the parent node should we insert a child, right? So, and we probably don't want to kind of traverse and pick an arbitrary position in the middle to insert a new child. So the easiest thing is really just to like in a stack to push the new child to the beginning of the list of child nodes. So let's see how we'll do that. So here is the add node method. It takes two parameters. The first is the parent node, and the second is a new node that will add to become the first child node of the parent node. So the parent node, let's say it's pointing to the node A, and in most cases, node A would have a first child already, and this first child can point to other siblings. And the first child also, its previous pointer is pointing back to the parent node. And the new node here in this case is the node B, and right now none of its pointers or references are pointing to anything. So let's see what happens after the first few lines of code is executed here. Now, the first thing it does is it does a validation, making sure that the parent is a node in the tree, right? And in most cases, it should be unless we did something really wrong. Now, the next 3 lines of code here is setting all the attributes of the new node, all of its references. Now, the sibling of the new node should be pointing to the first child of the parent, right? So that's this line. Now, the new node's first child, well, it's a new node. It doesn't have any child yet, so it's being set to none, and its previous, now that this node is the first child of the parent node A, it should be pointing, the previous node should be pointing to the parent. Now, the root of the new node should be the root of the tree that we're in. So that's why here it is set to self.mroot, which again is the root of the current tree. Now, all the references of the new node has been set properly, but the parent and the original first child, they still don't know the existence of the new node. So the next step is to fix that. So we want the first child of the parent now points to the new node, and that's what this line of code is for. And also the original first child, which is now the new node's sibling, right? The original first child has been assigned to the new node's sibling. So its previous pointer should now be pointing to the new node. Now, some of you would notice there is a conditional here that before it says the previous pointer of this node, it checks to make sure that the new node's.zip attribute is not none. So why do we need this check? Well, because it is possible that the parent did not have any child to begin with. In such case, the original first child of the parent, this would be none, and then the new nodes.zip attribute would be none, and if we just blindly dereference the dot previous of none, we'll get an exception. So we have to check to make sure it is not none before we do this step. All right, so regardless if we do this, the final step in this process is that now that we've added a new node to the tree, we should increase the number of nodes in the tree by 1. So now we have the basic tree instantiation method. We have method to set the root of the tree and methods to add nodes to the tree. We're ready to build a tree. Now, to do that, we'll actually create a bunch of nodes first. And these nodes, remember the important thing about them, or how to actually see which node is which, is by their label. And here I actually use the string standard package, and we'll go through all of its ASCII lowercases letters, which is basically the lowercase a through z, and I create 26 nodes. Each of those nodes will be labeled with a letter A through Z, and I'm going to assign each of these nodes to a dictionary nodes. That is, the key is basically just the letter A, B, C, and the values are the nodes. So we have 26 nodes that we can use, and we can reference them easily, and we'll insert them into the tree. Now, we only do this again because it's easier to identify them this way. We don't need them once we have data. So to build a very simple tree with just one node, we can just instantiate the FhTree and set the root to, let's say, the node labeled A. And if we want to add a child, let's say a node B, to the root of A, then we can just say add nodes A, that is the parent, and then nodes B is first child. Now that you have all the code we've written for a tree so far, and you know how to use them, I would hope that you can construct this tree by making a series of add node calls properly. So please pause the video and give that a try. All right, hopefully you have done that. Now, here's the code to do that. One thing I want to point out is because each of the new child is pushed to the head, let's say the head of the list of siblings. So in order to have, let's say, B as the first child of A, it would have to be the last child that is added to the parent A. So the order matters here if you want to have this tree precisely the way it is drawn here. Now, we've written a lot of code so far, but what if we just want to run something? What do we actually get to see? Well, right now, if we print out the tree, we don't see anything because, we haven't implemented the string method yet. So the way that we've been writing code, we've been writing a lot of code, but we didn't test or see that any of it actually works, is really the wrong way to develop any software. And I really do apologize for that. This is not normally how I would approach coding, but we will try to fix that in the next video by writing the appropriate string method so we can really see what we've put into the tree, and hopefully they are correct. In the next class in the series, let's say 3C, in which you will study data structure in more details, will hopefully show you the right way to develop code for data structures, and that is to test as you implement the code, or even perhaps write test before you do the implementation.